All right. Good morning, everyone. Let's start a new project today. So last class, I did share with you on GitHub the data in the partial code for this new exercise that I asked you to already get the code. So there was one script and two data sets, or three files for data. So two images and one shapefile for plots. I asked you to create this project called 13 Imagery VRN and create an RStudio project for that. So my assumption is that you've already done that, so we can get right into the programming side. So if you want to go ahead and launch that RStudio project, we're gonna get started there. Okay, so last class we went through the lecture and we were talking about how can we use in-season imagery, in this case here drone imagery, but it could be satellite as well, to assess crop stress and relate that to nitrogen, right? So if you recall, we talked about a few different algorithms, and one of the ones that I gave a little bit more emphasis was the Holland-Shepard's algorithm. So that algorithm takes into account how much nitrogen is required minus any credits, and then multiplies that by a sensor-based information, which is in the form of a sufficiency index. If you remember, that sufficiency index is the ratio of any vegetation index from a part of the field that may need nitrogen divided by that vegetation index from a part of the field that does not need nitrogen, or that we assume it's sufficient in nitrogen as our reference. So we're going to go through that exercise here. The data that we're going to be working with today comes from a on-farm study in corn. And we're going to talk a little bit more about this and really set the stage of how this was applied on farm and what were some of the outcomes of this prescription. Because here we're going to be making a prescription, and then we're going to see the effects of that prescription afterwards, because we also took an imagery afterwards to compare. All right, so really, if you're interested in how to collect drone imagery data and process that, we're not going to be doing that here. That is something that if you want to learn, Dr. Lorena Lacerda has a great course that she teaches. I'm not sure which semester, maybe in the fall, she teaches a course just on collecting imagery data with drones and how to process that imagery. And she also has some use cases in that class. This here is assuming that we've already collected that drone data, we've already created the orthomosaic, and now we're going to use that orthomosaic to make inference about nitrogen nutrition. So we're bringing in that process UV imagery in the form of NDRE. If you remember, NDRE is a vegetation index that we talked about in the lecture that uses the near infrared and the red edge band. We're going to create a variable rate nitrogen grid, which would be the grid that the applicator would use to vary the rate. We're going to calculate the required variables for the Holland-Shepard's algorithm. So if you recall, we need to calculate sufficiency index, which means we have to have a reference. So I think Ujwal had a question last time about, or maybe it was Neva, sorry if I don't remember who asked this, but somebody asked this about how can we set the reference value. We're going to be using here the concept of a virtual reference. Even though in this study here, they did have an actual reference in the field, but I want to show you how to create a virtual reference, as that is probably going to be the most applicable if you're working on farm. And then we're going to use all that to create an imagery-based variable rate nitrogen prescription, export that prescription, and finally validate that prescription by bringing in an imagery after a few weeks after application and see what were the implications of that. All right, I left you here. The first chunk is just all the packages we're going to be using. I believe you already have all these packages, so there's not much to do there. Just make sure you run that chunk. Map tools not installed. Okay, so if you don't have map tools, you can just give it an install.packages map tools. So let me. Oh, so if you install it doesn't work. Okay, so for now, you can just comment off map tools. I don't remember specifically which function of that package I was using in the script. But since I have map tools, I will be able to run that chunk whenever we get there. And you, on your side, if you don't have map tools, you will not be able to run it. So whenever we get to a point of the exercise where it works on my side, it doesn't on yours, it may be because of that. So just let me know, and then we'll troubleshoot from that point on. All right, so for now, if you don't have map tools, you can just comment it off and then run the setup chunk. The next steps here are going to be for us to bring in our drone imagery. So I share with you two drone flights. One was pre-VRN, one was post-VRN. So because our goal here is to imagine that you went to this farm, the grower wanted a variable rate nitrogen prescription. You flew the drone today, ran this whole script, gave them this prescription, and then tomorrow they applied nitrogen. That's what we're going to be simulating here. So we're bringing in the pre-VRN imagery first to create our prescription based on that. We're going to use read star. So this is a TIFF file. I don't know if you notice, it is a TIFF file, which is a raster file type. Remember that there is a difference between file types on your file system and objects in R. So TIFF is the file type on your system. When we bring that in R, we're going to be treating that as a stars object. So we're going to use read_stars. So one thing that we're going to do here, so within this read stars, let's just give the quotation marks, navigate outside of the code folder, go inside the data folder, and bring in the NDRE pre-V12. So this image here, if as you read that, it is, it has a very small pixel size. I believe this here is like, well, you know what, I'm not sure. This should be in meters if the CRS is correct. Yeah, so the CRS here is projected, so it is in meters. So the offset here is that resolution, which is in some 0.1 meters. I do want to make this coarser for a couple of reasons. One of them is that it's going to help us to visualize this. If we use map view to visualize this layer, it's going to take a little while to run it just because it has so many pixels in this image. And also because for nitrogen, we really don't, if you imagine, you're never going to be able to change a nitrogen rate every 10 centimeters. There's no equipment that can do that. So it doesn't make sense for us to have such a fine resolution in this case. And just to make it easier on our processing side and make things go a little bit faster, I just want to make this coarser right here on this chunk. To do that, we can give it a pipe and use a function called st_downsample. So this is going to make it coarser. And then it has an argument for n, which is how many times you want to make it coarser. I want to make it equals to 3. So if we run that, and then you print it now, your delta here, it has increased in 3 times. So now your resolution is about 50 centimeters, which for nitrogen is plenty. And then lastly, I just want to make something here to help us when we're coding with this layer, because right now the only information we have on this layer is NDRE pre-v12.tiff. This is kind of like the name of the column if you think of it. I want to simplify this column name here so it's easier for us to reference it. So let's right there on that chunk, give it a pipe. I want to use the function rename. and I want to call this just NDRE. So NDRE is the new name I want to give it, equals the current name. So the current name is that NDRE pre-v12.tif. So if you run that and you print it, you're going to notice on the first panel that we have NDRE as the name of this variable. And then we have our resolution also coarsened to about 50 centimeters. All right, the next thing is I want to bring, so this was a non-farm study. So it was a trial, it had treatments, it had replications. So meaning that we had plots. I want to bring the shapefile of those plots into R so we can also use them and look at them on this next chunk here. So if we come here, we're going to use a read SF, right? Because remember that plots boundaries are vector geospatial files, and the one that I share with you on your file system is a GeoJSON, which means that when we're bringing to R, we're going to treat that as an SF object. So quotation marks, we get outside code, go inside data, and then bring in the plots.geojson. If you just run that and we print it, it is a simple feature collection of polygon, WGS84, UTM zone 14 north. Just for your reference, this UTM zone 14 north is not a mistake. This field is in Nebraska. That's why it's a different zone than what we've been working here in Georgia. If you go on the data side, it has all these columns: ID, treatment, rate, area in meter squared, an acre, and then a geometry. I do want to just standardize the name of these columns to be all lowercase. For that, we're going to use the janitor package. I don't think we loaded that package above, so we can call it by just typing janitor, : clean names. That's the function I want to use. Okay, so now our column names have been standardized, all lowercase, easy to refer to them when we're coding. So this treatment column here, let me tell you what is going on. So we have here a reference, we have grower levels, and we have sense levels. We're going to plot this in a second so you actually see what they look like, but I just want to tell you what this was. So this study here had 3 treatments. One of them, the reference, was a high nitrogen rate being applied. You can see that here on the rate pound per acre. So this was corn, just for a reference. It was an irrigated field in Nebraska. It was a high yielding field. So this crop here was receiving 250, or the reference treatment was receiving 250 pounds of nitrogen per acre. And this was, for that study, it was used as the reference, right? So whenever we're making this recommendation for nitrogen, we need a reference. That treatment was defined as the reference in this study. Then we had a grower treatment. So this study, this treatment here was basically whatever that grower was doing as their traditional practice, which in this case here was applying 145 pounds of nitrogen to the corn. And then there was a sense treatment, which was receiving no nitrogen rate in this case here. And the sense treatment is basically the one that used the drone imagery, created a prescription, provided that prescription to the variable rate applicator, and that was applied to the field. So those were the 3 treatments in this study here. And then this rate is what was the fixed, already applied pre-plant rate or at planting rate. So all these rates here are being applied at planting, and then around V12, so when corn has 12 fully developed leaves, they came, I don't think the reference received any more nitrogen. The grower applied whatever their own rate side dress was, which was a rate, but is not reflected in this data frame. And then the sense rate on side dress was being dictated by the sensor data. So this column here, rate pound per acre, is whatever was applied at planting or pre-planting. All right, so let's go ahead and make some plots here, make some EDA, so we understand what is going on with this data. If you remember, if I have a raster or if I have a stars object that I want to make a map of, I can plug that right into ggplot and use geom_stars for that, which we're gonna do here in a second. But before we do that, I want to look into the statistical, not spatial, but statistical distribution of NDRE for this field, which we've done a lot of times for different variables in this course, and we always use geom density for that. Now, geom density is not going to work with a stars object as is. Remember, a stars object, to make a map of it, works with geom_stars, but geom density is not going to work right off the bat. So this pre-NDRE is our stars object. We need to kind of extract the data frame from it. So whenever it is in a data frame format, it feeds into ggplot and we can use any other geom with it. So let's go ahead, add a pipe here. I'm going to use the function as.data.frame. If you just run that, this is what you get. So you get an x coordinate, y coordinate, and NDRE value. There's a whole bunch of NAs that we're seeing here, which I'm assuming are the ones outside of the field, but inside of the bounding box. We can just plug in a summary. Can you say that again?
I would say like
All NAs. So for me here, I have values, but it's always also saying that there's like 108,000 NAs on the summary. So maybe let me get a tally, like how many rows. Okay, so there's like almost, 660,000 rows. Out of those, about 100 and some thousand. So 108,000 are NAs. So that's why we're seeing a lot of NAs when we just turn that into a data frame, is because there are a lot of NAs and they're coming up first in the data sets. But we can ignore that. This is basically just data points that are outside of the field, but inside of the bounding box. Because again, this is a raster file, if you remember. All right, so let's just plug that into ggplot. So if I want to do a density plot on the AES here, I just specified the X variable, which is going to be that NDRE column. And then, and then a plus, we ask for geom_density. So this is what we're seeing here. It looks pretty normally distributed. The mean NDRE value is probably somewhere around 0.28. We have some values that probably go just below 0.4, and we have a lot of very low values here going even below 0.1. So I always like to look at this distribution of the data just to get some idea of what's going on. All right, so the next thing is I want to make a static map. So a static map, right? So I do want to make a map out of this that I can show I can actually see this, the data spatially in the field, and then having color by the NDRE value. So I left you here this. Yes.
But could you scroll back up just momentarily?
Yep.
Yep. All right, I'm good. Got it.
Okay, awesome. All right. So now let's make a map here to visualize this data in space. I want to do a static map first, so we're going to be using ggplot. I left you here some of the code. So we're going to be creating this map and assigning that to this object called pre-NDRE map. So we can call this object again later in the script. But I left you some dots here for you to help me with. So if you just run this now, it's going to give you an error because R does not recognize those 3 dots. That was just me making a placeholder for us to fill in together. All right, so look at this code. And I would expect for you to know what is missing in at least one of those three dots. The other one, it's okay if you wouldn't remember, but the first three dots here, I would expect for you to know what is missing for us to make this map.
The geom is missing.
The geom is missing, right? Which one? Which geom?
I would say SF if you're gonna work with the image.
Okay, so if you remember geom_sf, we use for vector files, right? So if we were plotting the plots object, which is an SF object, we would use geom_sf. In this case here, we're plotting a stars object, which is coming from a raster file. So we're using geom_stars. And then all we have to say here is just say data equals to, and the name of the data set, which we have above, which is called pre_ndre. Don't forget to add a plus at the end here so it connects with the next row. And for now, what I want to ask you is if you just add a comment in front of the three dots here, so they don't get interpreted by R, and you run what you have. So if you run that and make a map, this is how that looks like. So you don't know this yet, but I can tell you that on this field does not look like this. If you like, the shape of it is kind of weird. If you recall, for some reason that I don't know why, when you plot geom_sf, it already sets your coordinates of the X and Y axis to match what it would be in space. However, when we do that with geom_stars, it does not. It tries to compress to the most, to the extent possible to try to like make it very concise of a visualization. So it's not respecting the actual shape of the field itself when we use geom_stars. That's what the second set of three dots here is doing for us. If we've come across this issue before, and the way that we fixed it was one of two ways. We either brought a geom_sf object. Let's say if we had the field boundary, which we don't, we could bring the field boundary as geom_sf, and that geom_sf would force it to be displayed properly. In this case, we're not going to do that. We're going to change the coordinates on ggplot. So there's a function called coord_equal. So that basically has the same effect. It's gonna set the coordinates to have equal spacing here. And so it's not gonna compress the plot for us. So if you just add the coord_equal, make sure you add the plus sign. This is how this field looks like. It is a part of a pivot. So as one side of the pivot is under this study here. This is how this imagery looks like for this field. So we're visualizing here NDRE, where the dark blue color is lower NDRE. So that would be lower crop vigor, potentially even soil. Although at this point here, I wouldn't expect to see a lot of soil. So this, just to give you a little bit more background. So this imagery was collected at V12. So corn was already, the canopy was already closed. So unless there was, for some reason, no stand, no crops growing in any of these parts, unless that was the case, I would not expect to have a lot of soil pixels. So we can think of NDRE low values here being mostly parts of the field where the crop is going through a stress. And then the yellow side of this color scale is very healthy corn. So we can really see some patterns here. Right, so I wanna, well, before I tell you much more, I just wanna ask for your thoughts. What do you see, what patterns do you see in this imagery? Dalton, what do you think?
Looks like it kind of, you got like a planter pass or something to do with the width of the implement.
Okay, so on the east-west direction, right? Seems like we have a pattern
Yeah.
there. Yes, I agree with that. Anyone else is seeing more patterns? Or Nelisa, what do you think? The same? Like running north-south? Yeah, I agree. Yeah, so Renelisa here was saying that she's also seeing some north-south direction patterns here. Awesome, thanks, Renelisa and Dalton. So yeah, when we plot our plot shape files here, you're gonna see that the plots are running east-west. That is the pattern that we see on the east-west direction are the plots, which means that different plots receive different treatments, right? So that's why we see this east-west gradient, and the north-south gradient we also see here is going to be associated with the field itself. So it's going to be underlying soil variability that is impacting the response across the different treatments here. All right, so I want to make quickly a interactive map here. So this is, we're not going to do a lot of customization. It's going to be just to get a sense. Let's use the function map view. So this is coming from the package map view, which you should all have installed already. And then we're just going to call the object pre-NDRE. If you run that, at least on my side, the way that it shows up is with the base map of, I don't remember what was the name here, but it's not the satellite imagery. We can change that easily, and it's going to be useful for us to change that. So if you come here on the stack, you just select the Esri world imagery. That's going to change for a satellite imagery base map. So again, this is a field in Nebraska in the Midwest. If you're not familiar with the Midwest, if you zoom out, you're going to see that there's a lot of irrigation in this area. Nebraska is one of the most intensively irrigated row crop areas in the world. So there's a lot of pivot shapes when we look at the satellite imagery. And differently from Georgia, the way that, and of course, this is because of many different reasons, but one of them that it's a lot flatter in the Midwest, especially in Nebraska. So the way that the fields are configured is that they are on a given grid. You can see that they all have the same size, the same shape. They're all looking very similar, which is not something we have here in Georgia. We have fields that are very, they're not as homogeneous in size and or shape. So we have more variability here in Georgia to work with. But anyways, this was a study again that was running one side of this pivot. What I want us to just play around a little bit is if you're looking at this and you come on the site and you turn on and off your pre-NDRE layer, I hope you can see that so those streaks of lower NDRE that we see going north-south have some underlying soil behind it. Some underlying soil variability behind it that we can tell from the satellite imagery. Right, so this is the type of variability that we wish that imagery can help us address. So imagine that whatever this is, maybe it is an eroded area, maybe it is just a different soil type that for some reason is creating different potential of crop growth and yield potential as well. So we can really see that on the satellite imagery and also on the effects on our drone imagery here of corn growing, in this case, at V12 stage. So two sources of variability on this, on how the crop looks like to a sensor. All right, The next thing I want to do is just add the, make a plot of the treatments of the plot, or make a map of the plots. So let's go ahead and use ggplot here. Gonna add a plus. Now this is an SF object, so we're gonna be using geom SF. Data is gonna be equals to plots, which is the name of the object when we imported that. And I do want to have on the AES, I want to say fill equals to treatment. So TRT, which is a column in the plots object. We have that TRT column so we can visualize the treatments. So this is how it looks like. Again, what you can see here is we have 3 treatments going east-west. The blue one here is the sense. So those are the strips that receive variable rate nitrogen application based on the drone data. We have 1 strip for reference, and then we have many strips for grower, which are the red ones here. So this is how those strips were set up in this field. You can see that they are replicated and randomized. This is a study. So that's important to have.
Question, could you scroll back up to the code for a moment?
Mhm.
All right, thank you.
And again, I'm giving you the plot shapefile already. We did not make that ourselves, but this is something that, of course, had to be done previously, so they would know where each treatment would be going on this field, and then be able to create the prescription afterwards. All right, so I think we talked a little bit about this, of all the what the treatments were. So the grower was whatever the grower was doing, which was applying a given nitrogen rate at planting, in this case 145. The reference was a high nitrogen rate at planting of 250 pounds of nitrogen per acre. So we could have that condition of knowing that the reference was not stressed by nitrogen, at least. It could be stressed by other things, but nitrogen was not the limiting factor in this case. And then we have the sense strip, which is basically what we saw. So on last lecture, we saw this system working, right? So I showed you a video of this system actually going through the field, using the active proximal sensors on the boom, sensing the crop right there, making a decision on the rate, already applying the rate with that high clearance applicator right there. So the sense treatments here, they were actually applied treatments, but they were applied using the active sensors mounted on the boom. They were not applied based on the drone imagery. However, this data was collected, drone data was collected on the day before they actually applied the treatments in a way that we could create this prescription from drone as well if we wanted. That was part of the study as well, comparing different sensors. So just so you are aware, the sense strips, again, they were treatments that receive variable rate nitrogen application based on the active sensor mounted on the boom. So not on the drone data, but we're going to simulate what would have been the drone rate that would have been applied if we had used that data set to create the prescription. All right, so, and one of the reasons why we're doing this is even though that setup of the high clearance applicator with the active sensors mounted on it, with the variable rate controller, are all commercially available. So if a grower wanted to implement this, they could do very easily. However, there is a cost to the sensors, which I don't know how it is today, but at the time it was probably about $5,000 per sensor, just the sensor. What if you're a grower that you do have variable rate capacity, so you have equipment to do variable rates, but you do not have the sensors, but you wish still to be able to apply variable rates? That's why we're bringing the drone here. And that's why maybe we could even bring a satellite imagery here, because then the cost for the grower is a lot lower. And they can still make a variable rate application, but not having to invest that much money on the sensors. So 5,000 one sensor, you probably want to have, depending on the length, on the width of your boom, you may want to have 4 sensors. So that's $20,000 right there. So if you can save that money you know, by using a drone imagery or maybe a satellite imagery, that's even better. So one of the differences here, there's a couple of them, and we talked about these when we went on the lecture on the pros and cons of some of the different sensing platforms. But one of the differences here is that if a grower has the high clearance applicator with the sensors mounted on it, it's sensing as it's moving through the field, is already making a decision based on the algorithm and already applying right there. So for the grower, it's very little know-how needed. They don't have to get imagery, they don't have to process imagery, don't have to do all that we're doing. It's all happening right there within the system. In this case here, if we're using a drone imagery, there is the complexity added of that. So you need someone that needs to know how to do all this, like what we're going to learn. But also means that we cannot sense and apply on the same pass as it is in the case of using the active sensor mounted on the boom, right? So here we have to fly, process the imagery, create a prescription, feed that prescription into a variable rate equipment, capable equipment, and then do a pass to apply that variable rate map, right? So it's like a two-step process if we're using imagery of any sort, in this case, drone imagery. Also, another difference here is that we need to, so the imagery, imagine that now we have pixel sizes of 50 centimeters. It makes zero sense to give a grower a variable rate nitrogen map that varies a rate every 50 centimeters, because no equipment is going to be able to handle that frequency of changing rates. So in our case, we're going to have to create a grid of a certain size. And on each cell of that grid, we're going to basically take an average of the NDRE values on it. So we make it coarser, and that grid cell size also becomes the size that the grower is going to apply that or change the rate across different cells. So let's go ahead and make a grid for that purpose here. We have made grids before in this class. This one's going to be a little bit different from what we've done before. So here's what I want to do. I want to take the shapefile of our plots, right? Which was this one here. And especially for the sense treatments, I want to chop it up into smaller pieces, right? So let's say I want to chop it up on the swath. So the swath here or the width of the plot is already reflecting the width of the capacity of the applicator. Now I want to chop it up into certain lengths. So let's say if I wanted here to have a smaller chunk every 6 meters, which is what I'm assuming that equipment can handle, is changing a rate every 6 meters. And this 6 meters here could be different, could be a higher number, could be a lower number. It will depend on the equipment itself. But I want us to use 6 meters as the length of that pass that a different rate can be achieved. So let's get to coding here. Let's begin with our plots object.
One pass is one tribute.
So I believe it was more than one pass, the width here. I don't quite remember the width of this strip, but I guess for purposes of simplifying, we can assume that one treatment here was one pass of the equipment. I don't think that was fully the case, but that's how we're going to treat this when we create the grid, assuming that one pass is one pass has the length of the strip or the width. All right, so we start with the plots, which is the object above. If you come after that comment there, we're gonna make a grid. If you remember, we've used this function already. It's called st_make_grid, where we need to say what is the cell size. So we give here two numbers. One is gonna be the length, one is gonna be the width. So I want our length to be, again, 6 meters. Our width, what I want to do here is have a very long width in a way that we create a grid that cuts through the entire study, okay? So I'm just gonna use a number here of 1,200. And we can, let me see here. I don't think I have a chunk here, but let's just create a new chunk to make a plot of this so we can see what is going on. We can even just do a map view, but oops. Map view of the grid VRN. This is what is going on. Actually, I guess 1,200 is even way too wide than what we would need for this field, but it was just, I wanted to go beyond it just to make sure that we do not have issues. So imagine that this grid here, I want to have these cells that are, so if you're going on the east-west direction, that they are 6 meters in length, but very wide, because I want to intersect these cells with our plots and chop it up those plots by each one of these cells here. So that's why I'm using 1,200 width of this grid, just to make cells that are very wide, to make sure we cover the whole extent of the field. All right, so another thing that we can notice here, and this is something that is really, really important for Georgia especially. Let me add a plus at another map view and bring our plots. So this field, the field here is a little bit tilted, right? So the grid is making a grid that is perfectly north-south, like it has I guess a 0 degree slope or whatever that would be called, right? So the grid is very straight on north-south direction, and the field is a little bit tilted. Here in Georgia, our fields are going to be a lot more tilted than this, or that direction of the pass is not going to be perfectly east-west. So I just want to make this grid to have the same inclination or the same steepness of the degree that the field is. So we're going to shift that a little bit, this grid a little bit to this direction, just to make it match the field slope, or not slope, but the field angle here. So to do that, we're going to first have to transform it to an ASP object. Remember, we've done that by using the function as, and then within it, we open and close quotation marks and call spatial. So when we do this, and if you just print grid VRN, it becomes an ASP object of type spatial polygons. We have not worked with these objects a lot for a reason, but to use the function that we need to use to tilt it, we're gonna need to have it as an ASP object. So if you add a pipe now, we're gonna use a function. Oh yeah, okay. I think this is the function that comes from MapTools. We can try it. So so the name of the function is elide. Yeah, this is coming from MapTools. So if you were not able to install MapTools, we can just skip this. So it wouldn't be ideal, but just so we don't spend a lot of time trying to troubleshoot that, we can just skip the rotation of the field. I will rotate on my side, just so you can see. You don't have to type this code because it's not going to work on your side, but I will show you here how I would do it. And then in the future, if you want to troubleshoot the installation of the MapTools package, then you can also use it. So the function is called elide. So it has an argument for rotate, which is the angle you want to rotate. So again, this field is not terribly tilted, but the angle that we're going to rotate here is -2.2. I found this number by trial and error, pretty much. It was just changing the angle and seeing until it matched the angle of the field. For this to properly rotate, we need to give the center base on which is going to rotate, right? So the center has to be the right in the center of all the plots. So if you think about it on this map here, the center should be right in the middle of all these polygons. The problem is that right now we don't have that. So if we had a boundary, it could be the center of the boundary. I did not bring you or give you a boundary. I just gave you all these plots. So to get the center across all the shapes on the plots object, we're gonna have to do something extra. So I'm gonna start with plots. I'm gonna ask for a function stUnion, which if I just run plots stUnion, it's basically going to merge all of those plot shape files into one. So it's basically giving me the boundary to some extent. And then I pipe that into a function called stCentroid, which right now plots followed by stUnion is one shape file of the whole field. So it's kind of like the boundary. But now I want the centroid of the boundary, right? I want a point to tell me what is the center of the boundary. So I use stCentroid. If I just run this to show you, this becomes then a point instead of a polygon with just a single point representing that centroid. But this centroid, the coordinates of that centroid are in the geometry column, which I need them to give me the number. I need the number, not of the coordinates, and not to have the coordinates into the geometry column. So I'm just gonna pipe lastly here stCoordinates, which extract the coordinates of whatever, in this case here, is the centroid of the field. So all this is gonna give me the center of that field, those two coordinates, X and Y. So that's what I'm giving here as the center points. So if we run all this grid VRN, I mean, we can go ahead and plot that again just to see what has happened here. Oops. So notice how now I still have the grid, but it has been slightly tilted, right? So now it's not perfectly 0 degrees in the north-south direction. It's a little bit tilted. And if I show that with the plots, we're gonna see that, oh, CRS not found. Okay, I still have to do some more processing here, but anyways, if you just notice now, it has tilted the field slightly. If you're doing this here in Georgia, I've done some of the work I've been doing. Fields are, I always have to use this function here because my fields, the direction, the AB line angle is always tilted, right? Which again, is not always the case in the Midwest because of the way the fields are. Anyways, so we just made that rotation. I want to, I guess on your side, I will tell you what you have to do. I don't think you would have to do this necessarily. But on my side, I need to set this as an SF object again. So I'm going to do st as SF. And then I'm going to assign the CRS because it has lost the CRS as we just saw below. So st_set_CRS, and the value for this, the EPSG file for this CRS, which again is in Nebraska, is 32614. After doing this, if I just print grid VRN, it's back to being a simple feature object. It has the proper CRS. And now if I just plot this, you can see that the tilt, I guess, or the angle of how the grid is tilted is matching the field as well, the passes of the field. So on your case, you really, let's see, the next thing here, we're just cropping and filtering. So on your case, you can just comment off or just delete, if you wish, all this code. So you're starting on as spatial and then ending on the st set CRS. You can just either delete or comment off all of those lines. So on your side, you basically make the grid, add a pipe, and then you want your pipe to connect to the cropping to plots comment, which is what we're going to do now. So we just created this very long grid, right? But I still want to crop this to my plots. So that's going to do two things. So one is going to cut this grid only to the extent of my plots. and at the same time is gonna chop up my plots into these smaller pieces. So for that, it's just a function called st_intersection, and we just give the plots object here. So if I run this, oh, in my case, I forgot a pipe. If I run this, and then we just plot this with the map view. I mean, really, we just need the grid VRN at this point. This is how that looks like. So basically, we intersected that long grid with our plots. And you can see that all treatments now have been chopped up in the slices of 6 meter length, if you think length going east-west. And because the treatments were already in place, the width is the width of whatever the treatment pass was. Now, lastly, because we're doing VRN only on the sense strips, I just want to keep those treatments, right? So I don't need to keep all of the other treatments like the reference and the grower because they're not going to be receiving variable rate nitrogen. So let's add a pipe here, and I want to ask for someone that has not helped me yet today to tell me how would you do that? If I just want to keep the sense treatments, which again are the ones that are receiving VRN, what do I need to do here?
Hey, Dr. Bastos,
Yes.
here in Tifton, we got errors with the intersection plots.
What is the error?
Mine says, no applicable method,
For intersection.
no applicable method for SD intersection applied to an object of class C spatial polygons.
Okay, is anyone else getting that? You're also getting the, okay, so, all right, so Ujwal here is saying that if you uncomment the ST_SSF, that should work. So try that and let me know if that works.
Yeah, we
Yep.
got it.
Awesome. All right, anyone else having issues before I ask again the question of. All right, I don't hear anything, so I'm assuming you were all able to catch up. So now, if I want to just filter the sense strips, so just the ones that are receiving variable rate nitrogen application, what function do I need here? How do I do that? Filter, okay, so Sundays set filter. Then what? Treatment TRT, right? That's the name of the column, equals to sense. Yes, oops, I misspelled sense. That's right. So if we run that and we printed, now we have 759 features. Those are each one of the cells within only the sense strips. Right, and if I just plot that using map view here, again, we're gonna see that we only kept those strips for the sense. Yes, Doug? With the filter? Okay, so it sounds like a similar error of what the guys in Tifton were having. So I guess the solution, at least for them, was to have the ST_SSF active in the code before you get into the intersection. So try that and let me know if that works.
Yeah.
Okay, awesome. Yeah, so if you see here now, we only kept the strips that are receiving VRN, and they are chopped up into 6 meter chunks that we're gonna basically create a variable rate for each one of these chunks. All right, so moving on here. If you remember, for us to come up with a variable rate nitrogen prescription using the algorithm that we saw in class, we need to have a reference value, right? So let's go ahead and create that reference value here. The way we're gonna do that in this application is to get one reference value for the whole field. That is the simplest way of doing this. If you had zones for this field, you could get a different reference for each zone. But in our case, we're gonna assume one reference value for the whole field. All right, so, again, the concept that I want to introduce here is to use a virtual reference. All right, so let's think about, again, what is a virtual reference? It's basically when you have in this case here, NDRE values for the whole field, you create a statistical distribution. So think of it as looking at the density plot of NDRE. And then you're selecting the 99th quantile of that statistical distribution as your reference value. So that is the concept of the virtual reference. Now, how can we do that in coding using some functions that we have already seen in the past? So the task here is extract the 95th quantile of the distribution of NDRE for the field. What function do we need here to do that? Rolando, any thoughts?
Nothing comes to mind, Professor.
Right, let me see if Niva, do you have any thoughts? Quantile, yes. Okay, so Niva said quantile. That's exactly it. So we're gonna use the function. So here on this chunk, you just give the assignment symbol. Let's use the function quantile. So I want the quantile of the NDRE of this field. The NDRE is part of that raster object that we brought. So the pre_NDRE. If we use the $, we can access just that column NDRE by itself. So if we were to print this, it would be a matrix with all the NDRE values for that column. We do have here an argument for probs, which is the quantile that we want to extract, which is the 95th, right? So probs would be equals to 0.95. So this number here varies from 0 to 1. And then because we have so many NAs here, if you remember quantile, the mean, median, minimum, maximum, ST, all these functions, if you have NA in the column that you're asking for that statistical summary, it will throw you errors. So to avoid that, we have an argument called na.rm. So remove NAs, we need to say true. So we're extracting here the 95th quantile of the NDRE, removing NAs first, and assigning that to this object called vrnref for reference. So if we do that and you print it, the 95th quantile of NDRE for this field represents an NDRE value of 0.31. That's going to be the value of our reference. Again, using the virtual reference concept. I think I left you here all the code of the next chunk, just so we can visualize, again, the density plot of NDRE and add a vertical line with geomv line where the x-intercept is the reference value, so we can visualize that in a plot. If you run that, this is what you should see. You already had all the code there, so nothing to do extra, but this is where the reference value would be set on this distribution. So imagine that now all the data points that are to the left of this line are going to be, I guess, Doug, I just want to show this here so we can catch up, because otherwise you won't. So you just need to copy this part of the code. So so we're basically using that value as our threshold. Anything that is less than that is going to be receiving a nitrogen rate of some level. Everything that has an NDRE value larger than 0.31 is not going to receive a variable rate nitrogen, at least not based on the sensor. What happens in practice is you can decide if a part of the field is asking for no nitrogen, I'm still going to apply a minimum rate of some level, just to make sure I'm giving some nitrogen. But then everything else that requires nitrogen, you're gonna be applying a variable rate on this field. All right. So the next thing we have to do here is, so let me bring a couple of layers here to your attention. So we have this layer, right, where we're going to be creating a variable rate prescription for each one of the cells that we're seeing here. That's the grid VRN object. We also have the NDRE data, the actual data from this layer, right? Which within each one of those chunks that we're gonna be performing VRN, there's gonna be many pixels in each one of those chunks. So what we have to do next is to average the NDRE values within each one of those little chunks that will receive a variable rate. That's gonna be our next step. So let me go back to the chunk. So if you come here on this chunk, we're gonna do that and assign it to this object called grid NDRE. So first thing here is we're gonna start with the pre_NDRE data frame. We're gonna pipe it and we're going to crop it to the grid that we created. So to do that, we're gonna use a function called st_crop. And we're gonna give here the grid_VRN object. If we run that, and we print this object here, grid NDRE, it's still a raster because we're starting with the raster and then cropping. But it has been cropped with the grid that we created. So let's go ahead and visualize this to understand what actually happens. So I left two I guess placeholders for us to complete here. The first one, so I want to make a map with ggplot. I want to show you this object here, grid NDRE, which is a stars object. So we're going to be using here geom_stars because of that. We're going to say data equals grid_NDRE. If we just run until this point, so if you don't add a plus and you just run until here, just so we can visualize what happens, here's what happened, right? So we basically cropped that whole NDRE image to just the strips that will receive variable rate, which are the ones that we really need NDRE data for. And now just to help us on the visualization, I want to add a plus, and we could use the chord_equal just to make it easier. The other alternative is we could bring in the actual, the grid VRN itself, right? So we can add here another geom_sf and say data equals grid_VRN, which remember that is our actual grid. And just say fill equals NA so we can see through it, and just add a plus there to connect. So if you run this, this is what you should be seeing now. So we have, again, we still have the NDRE values at the 0.5 meter resolution. So you can definitely tell that within each one of our chunks here of variable rate grid, we still have many pixels in them, but at least we have cropped to only the strips that will receive variable rates. All right. Now our next step is going to be to average these all the pixels within each one of those cells to have just one NDRE average value per pixel. And that's going to be our field vegetation index. If you remember on the SI sufficiency index, it was basically dividing the field vegetation index by the reference. We already have the reference. Now the field is going to be the average of each one of these cells that will be receiving a variable rate of nitrogen. I think this is just some text saying what we just talked about. So to extract the average NDRE of that raster layer for each one of the cells, we're gonna come on this chunk here. We're gonna assign that result to this object called grid NDRE AV for average. You can get the assignment symbol. We're gonna start here with grid underscore NDRE. If you remember, grid NDRE is that stars object that we just plotted above. So this is grid NDRE, the raster of that. Now to extract any statistical summary, if you've been using other GIS, this is called zonal statistics, right? So if you're using ArcGIS, QGIS, I believe, well, ArcGIS calls it zonal stats. I think QGIS as well. But in R, we're going to use a function called st underscore extract. So this is basically what a zonal statistical tool would be doing for you in R. Where we give here what is the shapefile that we want to extract something over, which the name of that shapefile, the grid, is called grid underscore VRN. We just did that above. It has this argument for fun, which is a shorthand for function. This is where you would tell what is the statistical summary you want to extract. In our case, is the mean, and we're just going to say here the name mean, no quotation marks, no parentheses. This is how the function works. If you wanted to extract the median, the minimum, maximum, standard deviation, whatever it is, you would change that right here. And then it has an argument to remove NAs as well. Remember, we have to do the na.rm equals to true. So if you run this, I guess it may take a quick moment here. I want to show you what that looks like in a second. I think on my computer, it may take a little bit longer than on yours because I'm using Zoom, or I'm sharing my screen via Zoom. Yeah, okay, so we went through. If I just print grid NDRE AV, it's still a raster, but now if we were to plot this, which I guess we can do that very quickly here, just do a map view on grid NDRE AV, just to explore what that is. Missing value or true false needed. Okay, I'm not sure why that's given that issue, but I guess we're just going to ignore that for now because we're going to be able to plot it in the next step here. But anyways, I guess the point that I wanted to make is that it is still a raster. I do want to create this as a vector because it's going to be easier for us to work with, especially with ggplot. So I just come here, add a pipe, and then call st underscore s underscore sf to force this to become a vector object type, in this case SF. Just gonna run that and let it go, let it do its magic. Just wait a moment here for that to complete. And so I just want to tell you what we're going to be doing next then. So on the immediate next code here, I just want to plot this. I guess it just went through. So let me print grid NDRE AV so you can see what it is. It is an SF object with 759 features. This is because we have now an average for each one of those grid cells that we created, that we have the average NDRE value. Now I just left you a code for a plot where I'm just plotting the results of what we did here, changing the color scale and so on. So things we've done in the past already. If you just run that and then you print NDRE map, this is what it looks like now. So basically we have averaged all the pixels within each one of these variable rate cells that we're going to be using. Now for each one of these cells, that value there is again our field vegetation index value that we're going to use into that sufficiency index calculation, which is what we're going to be doing in the next chunk here. So if you come to the next chunk, The goal here is gonna be to calculate the sufficiency index for the layer that we just created above. And assign that to an object called SI. So we're going to give it an assignment symbol. We're going to start off with this object here that we're plotting, which the name of that is grid underscore NDRE underscore AV for the average. We're gonna pipe that. So right now I'm looking at this and I have one piece of code here that I'm not sure why it's there. So I'm going to ignore for now and just tell you the next step. If things don't work for some reason, then I know the reason why. But okay, so on this data set, which again, it's a vector file, we have a column for NDRE. So remember, this is the VI of the field. We first have to calculate sufficiency index, which means we have to bring here the reference value. So what I want to do here is if you come on the setting reference, I want to do a mutate and create a column that's going to hold the reference value. So I want to call this column NDRE underscore ref for reference. And this is going to be equal to the value that we got for when we calculated the reference, which is saved under an object called VRN underscore ref. So if I just run VRN ref, this is just a value, 0.31. So I'm just creating a column here where it's going to hold that fixed value all the way through all the rows. So all the 759 rows here have the same reference value, which again is that 95th quantile of the NDRE distribution of the field. All right, so now let's calculate our sufficiency index. So let's give it a pipe. If you come after the comment here, calculating SI, let's call a mutate. I want to call this column SI, and this really is just that ratio, right? So I have a column that is NDRE. I have a column that is NDRE ref. It's just the ratio of those two columns. So my SI is going to be NDRE, which is the name of the column, divided by NDRE underscore ref. And that's our SI. So if you run that and you print SI, we have this column now that is called SI, and it has values that range from, anywhere from 0 to greater than 1, maybe like 1.3. All right, I do want to look at the SI map. So making a map, show me the SI value of that field. So if you come here on the code right below it, you remove those 3 dots. We're going to be using geom_sf. The data is going to be equal to SI. I want to call AES, and I do want to fill those cells by the SI value. So I say fill equals SI, and I just want to say color equals NA. So we don't have a null line color there. And just remember to add the plus so you connect with the remaining of the code. So let me show you the code if you're still catching up, or at least that part. So we have a map here that looks perhaps similar to what the NDRE map looked like, but now the range of values is different. So SI is ranging from about 0.5 to about 1 on this field, where a value of 1 means no or very little nitrogen stress. A value below 0.7 means you have, well, a value, I guess even a value below 0.9 means you have some level of nitrogen stress, but of course, the lower is the SI, the greater is the nitrogen stress. So we see here that we have some nitrogen stress on this west side of the field. We have across those strips that we were talking about being related to the soil effect. All right, so now we have SI. So the sensor piece of that algorithm has been calculated, has been determined. So now let's get to calculating variable rate nitrogen here. If you remember from our lecture, at least three pieces of information that we need to calculate variable rate were the optimum, the EONR, or the economic optimum nitrogen rate. This again is something that for this algorithm, you would be getting that from the grower. Whatever the grower normally applies to this field, that's the rate you would use. You would remove from that rate any credits of nitrogen that you already have in this field. In this case here, some of those treatments received a pre-plant application of nitrogen. So that would be a credit in that case. It could be from a previous legume crop. It could be from applying organic amendments. Anything that has nitrogen would go into the credits. And then we need the SI. So the SI we already calculated. Everything else is just a number that we can determine. So let's get into actually determining this variable rate here. Okay, so we are going to come on this object on the next chunk here. The object that we're going to assign this to is called VRN. So I left you some code there just to make it a little bit simpler for you, but we're still going to have to develop this a little bit more. So we're going to start off here with object SI. I just want to remind you what SI looks like. So it has 759 rows, which each row is one of those cells. It has a column for NDRE reference, and for SI. Really, for what we are concerned, we just need SI at this point. Let's give it a pipe and let's determine some numbers here, especially the ones related to that nitrogen balance part of the equation. So let's give a mutate. So if you remember from the algorithm, the way that the algorithm refers to the optimum nitrogen rate of the field, or the EONR in the formula, is referred to as NOPT, or N optimum, the optimum nitrogen rate of the field, which for this field here was what the grower said was 229 pounds of nitrogen per acre. So if we just run this, our VRN object now is going to have another column with NOPT that has the same value all the way down. Now, I do want to determine some credits here. So one of the credits we had on the equation was the pre-plant applied nitrogen, which in our case was 0. For the sense strips was 0, but I do want to set that column here. So N pre, so nitrogen rate pre side dress was set to 0, and then this field here had a credit of nitrogen. I don't fully remember if that's coming from a cover crop or a previous legume crop or whatever it was, but it has a credit. We can perhaps assume it's coming from a previous legume crop. So it has an N cred of 20 pounds of nitrogen per acre. So I know my optimum nitrogen, and I have two credits here where one of them is 0, the other one is 20 pounds per acre. If I just run up until this point, we have, or imprinted, I guess I forgot to print it. We have now our SI, our optimum, our pre-applied nitrogen, and our credits. So now we have all the pieces that we need to put this right into that algorithm. So I'm showing you here the formula for the algorithm. I'm just squeezing things so we can see together. So this is just, I wanted to give you a scaffolding of that so we wouldn't get boggled down by making sure we all have the proper parentheses in the right place and so on. But this is what the algorithm is the same as what I showed you on the lecture. So the algorithm has this first part of it, which is that nitrogen optimum minus credits part of it. And then you multiply that by the sensor data coming in the form of SI, right? I left you all 3 fill in the dots in this formula here related to that nitrogen balance that we calculate on the first part of the algorithm. So I want to ask for other people that have not helped me yet, if you, given these names that we gave here, how would you fit them into this formula? Doug, what do you think?
Optimum first,
Okay, so our optimum first, yes,
the credits in three.
exactly. So the pre, which in this case is 0, but let's put that there as well, and the cred. That's exactly it, right? So as we're doing this, we're determining how much we need total. We're removing any credits that we have in the system, and that gives us a nitrogen amount, which in this case here is going to be 209. And then we're adjusting that amount either more or less than that based on the sensor data. So if you go ahead and you run this chunk and you print, now we have a column here for VRN in pounds of nitrogen per acre that we have on this column. And each one of these rates is related to each one of those cells in that map. So if we just create a density plot of this so we can see the distribution of rates, if we run that, so we see here that some parts of the field are receiving just above 50 pounds of nitrogen per acre. The average of the field is probably around 150 pounds. And then some parts of the field are receiving beyond 250. Notice how some parts of the field are receiving more than what this balance here was. So this balance here was 209. Some parts of the field are receiving even more than what the grower would recommend. I want to make a quick parenthesis here. So in many ways, especially with nitrogen recommendation. So with nitrogen recommendation, the algorithms that we use for fixed rate, which are based on studies across a lot of locations and years, they are very conservative and for a reason, right? So they're conservative in a way of saying, hey, you may need only 100 here, but let's apply 150 just to make sure that if something happens, if you have lots of losses, whatever it is, you are covered. So those algorithms intrinsically incorporate that conservativeness, meaning that for precision ag nitrogen management, when we're using a sensor-based approach, we would most of the time be recommending a lower rate than what the fixed rate approach would, normally, most of the time. With that, the main goal of variable rate nitrogen management is not to increase yields, because there is no magic. If you're applying less nitrogen, you're most likely not going to increase yield, right? Just because it's coming from a variable rate approach. However, for nitrogen especially, the promise, I guess, of the technology is that you can cut down on rates without hurting yields. And if you're using less inputs and maintaining yield levels, you're being more profitable, you're spending less on that nitrogen cost, you're being more efficient with nitrogen, you're probably losing less of that to the environment as well. So again, some precision ag technologies, if you think of, variable rate seeding or planting different hybrids in the field, or really variable rate anything, you could either be thinking of that from the perspective of making the system more efficient by giving the same yield while applying less inputs, or maybe it could be the other way around where you could apply more inputs in fixed rates, but get more yield and more profit out of that situation as well. Again, in the case of nitrogen, because the recommendations that we use are very conservative, most of the time, variable rate nitrogen is going to be applying less than what the fixed rate approach would have been, but not always. So we see here, anything that's above 200 on this density plot is receiving more nitrogen than what the grower would have applied. So that still happens with nitrogen, but it's not the majority of the field most of the time. So I think that's an important point to make here. So really with nitrogen, our goal is, to what extent can we reduce rates without hurting yields, and therefore having less input costs, have more profitability levels, being more efficient with the use of nitrogen, and losing less of that fertilizer to the environment. That's most of the time what we're aiming here with nitrogen. All right. So I want to create a map of our variable rate prescription and assign that to this VRN map object. If you come here, I want to basically plot this VRN object, and just to remind you, that is an SF object. So we're going to need to change those three dots with a geom_SF, where the data is going to be equals to VRN. We're going to change the aesthetics here to have the fill being equals to VRN LBSAC for pounds per acre, and have color outside of the AS, have color equals NA, and then make sure you add a plus there so it connects through. So if you have, if you run this and you print that map, now we have a kind of like a mirrored, a flip side of the sufficiency index, right? So whenever we had a lower sufficiency index, we're going to have a higher variable rate being applied. And whenever we had a high sufficiency index, we're going to have a lower rate being applied. So they kind of mirror themselves there. All right, so if we come here on the next chunk, I just want to put both of those maps together. So the NDRE map and the variable rate map on the same, on this or side by side, so we can compare them. And then we have, I'm calling patchwork, so we can do that. All right, if you run that piece of chunk, this is what you would see. So let me ask someone that has not helped yet. Let's see, I think maybe everyone, or I don't know if Neva, oh, you did help me, right, Neva? I guess everyone has already helped to some extent. Well, Vinicius, let me ask you, so when we compare the NDRE map, which is the one on top, with the VRN map, which is the one on the bottom, what do you see there? What patterns do you see there?
Oh, I can see pretty much the same trend. And I can see the color is like opposite, which is not a good.
Where the plants are stressed, you put more nitrogen.
Yep, that's exactly it, right? So if we just pull some examples here, if I pull, looking at this patch of the field that has very low NDRE values, and we look on that patch here on the variable rate algorithm, we're applying more nitrogen here because it is more stressed, right? And then if we get the opposite, the flip side of that, so maybe if we look at these cells here that have a higher NDRE, meaning less stress, they are receiving less nitrogen as well. Yeah, that's exactly it. Thanks, Vinicius and Clint.
Question. With this, is there a way like you could set limits to how it applies like in certain areas in the field? Because if I remember right, looking at imagery where those I guess stress spots in the field were, there were like washes in the field. And I'm just thinking like here in Georgia, like if you have a really sandy spot in the field, the plants are always going to be more stressed. But if you put more nitrogen out there, it's not going to help, it's not going to help them keep up better.
Yeah.
So is there like a way that you could offset that?
That's a great point, Clint. Thanks for bringing that up. So there's a couple ways that we can do that. So in this case here, we're basically using a reference for the whole field. If we would have combined here, everything we did for the other field up until this point, as far as bringing EC and terrain and EO data, and we created zones, like actual, perhaps soil texture zones or something that relates back to your potential, and we had those zones, we could export one reference for each one of the zones. Not only that, but we could also set a different N optimum. So this value here could be different for different zones as well. Right? So imagine if you have zones in your field that have different yield potentials, it wouldn't make sense for you to even assume that a fixed optimum rate would be, I mean, that optimum rate would be the same across different yield potential zones, right? So we could change two things in the algorithm. One would be the optimum rate that you would apply to each one of those zones. So maybe if you had a low yielding zone, your yield potential is going to be lower, meaning that your optimum rate would be lower as well. So you're starting off with a different yield, optimum yield. And then on the SI side of things, you have a different reference value, so a different virtual reference value for each zone. This also determines, is going to allow you to be more flexible within the field that has different zones of yield potential. So that's how, we're not doing that in this exercise, but I think, you know, like we've done enough of other things that are related, that if you needed and wanted to do this, you have all the tools and you have the coding frameworks to be able to implement it. So that's how I would do it.
Professor,
Yes.
I got a question. Now, looking at that code, where the n pre is 0, if you just delete that one, since it was not doing anything, will the code still work?
So if you, let's say, if you just comment this off and then run, it's going to give you an error because you have this here, right? So it is looking for this column, but you never created it. So if you want to completely just remove that, you can, you know, comment this off or delete this line of code, but then also delete it from here. And then that should work. So another point here that kind of goes back or similar in the same direction of the question that Clint asked is, right now, this algorithm, the way that we set it up, is going to keep applying more nitrogen the lower it is the SI. However, there's going to be fields and there's going to be situations where a low vegetation index, which will translate into a low SI, is coming from maybe a part of the field where plants did not emerge, or maybe the stand was very poor, you have a lot of soil pixels, and you know that it's not going to help to apply extra nitrogen there because it's not going to respond. If that is the case, there is a way of addressing that on the recommendation formula. So if you were to come here, there is, so the original paper that published this algorithm, they have a Badcoff function, which is basically saying if your SI is less than a given threshold, which they propose a threshold of 0.7, then instead of increasing rate, you start decreasing. So there is a way to also control for that, right? Another thing that we can also think of it here is, so you allow the algorithm, you allow the plants to tell you how much stress they are going up through, and use that information as SI to determine the rates. However, you could still come here and say, come on this, if we look at this variable rate, VRN pounds per acre column, it's ranging from about, so let's say just above 50 and just below 270 potentially. Yeah. So let's say that I give this to a grower and they look at this and they say, well, I don't want my minimum to be, so the minimum here is coming from the sensor, right? It's not something that we're saying the minimum is 50. The minimum is coming from the sensor, from the algorithm. Well, let's say the grower comes here and says, well, I am not comfortable with applying a minimum of 50. In those places that are getting 50, I would like to apply at least, I don't know, 70, 80, 100, whatever it is. So they kind of determine for you that minimum boundary that they're comfortable with, right? After we calculate this, after we apply the algorithm, it's very simple, very easy for you to just come here, give it a pipe, and just do a condition, right? And say, if VRN is less than 80, then set VRN to 80. And if it's more than 80, just allow it to be what it is. I'm not gonna code that here, but it's also something very easy that you can establish both a lower boundary and upper boundary on your variable rate prescription just by adding a few if-else statements or maybe a case when in this case. All right, so continuing here, again, assuming that you're doing this because you are either applying this in your research or maybe you're applying this on a farming situation, we do need to export this prescription map so a grower can actually apply it. So let's go ahead and do it. The object that we want to export is VRN. Right, so this is the one that has the VRN in pounds per acre column. We're gonna give it a pipe. First, I want to select just the columns that are needed, so we don't give a shapefile to a grower that has many columns that may be confusing. So dplyr column select. We're going to select really just that VRN LBS AC. That's the only column that we need from this at this point. So if you just run this, you just get that column and the geometry. Let's give it a pipe, and we're gonna use write_SF, because remember, this is a SF object, it's a vector geospatial file. If we, I'm just gonna bring back here so I can see my files. Remember again, shape files have at least 4 to 5 accompanying files. To make it more organized, I want to come here on my files tab, go into the main folder of the project, go on the output folder, and I want to create here a folder where I'm going to save this shape file and all the accompanying files that come with it. So if you click on that plus folder button right there for us to create a folder. So right now I am inside output. I'm creating a folder called VRN inside of the output folder. And you need to create the folder first before you export, otherwise it gives you an error. So now if we come back to the code here on the write SF, we give it a quotation marks, we get outside of code, we go inside of output, we go inside of VRN folder, and then here I want to export this as a shapefile. I want to call this VRN.shp. And then as always, remember that on write SF, we want to change that argument called delete_DSN to be equals to true. So if you run this piece of code, I got a warning here, but I don't think I need to worry much. If I go on my files under output and I click on that VRN folder, I should see now that VRN.shp and also the other 3 accompanying files with it. And this would be the folder that you would send to a grower for them to be able to apply. Of course, I mean, here we're exporting the rate of nitrogen. The grower may need a rate of product, which you have to know from them what nitrogen source they're using, what's the nitrogen concentration of that, and then create a column here that would be rate of product and not rate of nitrogen. We've done that on the previous variable rate exercise that we did zone-based variable rate. You can refer to that if you need. All right, so moving on here. So we just exported this. The grower will be able to use this layer on their field. And on this case here, it was a study. And so the imagery that we used to create the variable rate prescription was obtained right before the site dressing time. But we did also fly this field at Tasselman. So this was probably, I don't know, a couple to 3 weeks after the first flight. We flew the field again to be able to assess the effect of the variable rate. So let's take a look at that on that imagery. So I'm leaving here most of the code. So basically bringing in using read stars, reading the NDRE post vt.tif, which was the other file that I shared with you, downsampling 3 times again, and then renaming as well, just like we did the first one. So if you want to run that, So you have this object post NDRE on your side. And then we're gonna make here a static map of the post NDRE map. I'm giving you here almost all of the code. You're just gonna have to change here the geom stars. So let's add here geom stars to bring in that post NDRE object. So we're gonna say data equals to post underscore NDRE. Just add a plus at the end. This should be sufficient. If you run that piece of code and you print it, this is what we see. I do want to plot these. Let's see here. I think we have a piece of code. Well, let's just run through this map view first of just that post application. So we can see, can again have that base map behind the scenes and compare. So if you go on the stack and change to Esri world imagery. Let me find a way to not have overlapping items. So if you just toggle that on and off, we can see that there is still that effect of the soil, the soil effect here that we see on the satellite imagery is still coming through on the post VRN application, right? So we still have that signal here. And I do want to go to the next chunk and compare both the pre and post VRN maps side by side. So these are both of those maps, I guess one on top of the other. So the first one is the pre and the second one is the post. Let me see, Doug, what do you see there?
And on the second one, the NDR is higher. It looks a little different, I guess, they look about the same, but the scale's different, but from what I can see on mine, it looks like the NDR over the field is higher than it was free.
Okay, so it's a good point, right? Because, so if you remember from the lecture, you will expect higher NDRE at future stages just because the crop is growing, right? So even if it is stressed, it's still gonna have more biomass than what it did a week ago. So overall, we would expect the field to have a higher NDRE at tasseling, which is the bottom plot, compared to the V12 one, which is the top one. Okay, what else? Anyone else has any thoughts here? Say that again? Okay, uniformity in what way? Okay, so we're not seeing anymore the east-west strips as prominent, right? And I agree with that. And that's because, you know, the whole field received nitrogen, but including the variable rate strips. What else? What do you think, Niva? Okay, so Niva is asking, why are there some trends like north-south? What do you think? So you mean, so what patterns? Yeah, but what pattern are you asking? Like on the map? Like, you mean this pattern? No.
For the world image.
Oh, yeah. It's a great point. My head was not even looking at that. So Niva is actually asking like this pattern here of like being at an angle. Let me look. It could be, I think it may be just the way that ggplot is showing.
I don't even see that one.
Could we not assume that would be like the cells, how we cut them? Kind of like in reference to the size, that the length that we cut them down to?
So I think that, so at least what Eva is asking is like these like tilted strips. I don't think they would be coming from the grid because the grid was not at that angle, right? It was a different angle. Neva had a question that could be the case, which is like the path, the direction that the drone was flown. That could impact. In this case here, I don't think that is the case. I think it's just on my display how that's showing. And the way that I was gonna check on that is to see if on the on the map view, if I still saw those streaks, and I don't see them. So I think it's just the way that ggplot is showing us that. But yeah, it's also a pattern that's there. So that's a good point, Eva. Thanks for bringing that up, because if we were to check on the map view and we also notice that same pattern, then it was a pattern in the image itself. And then it would probably be sensor related, right? Either the drone direction that was flown, maybe the time of day. I mean, it could be different things related to the sensing itself. But one thing that nobody said yet, and I just want to clarify here is, and maybe nobody said because it was very obvious, but we still have the very strong effect of soil, right? So the underlying soil effect is still coming through, which for this field, the way that this study was established, there was no way that that could have been taken care of, primarily because we only used one reference for the whole field. However, and that's something that we're doing in our research here in Georgia, and it's also related to Clint's question, is we're creating zones of yield potential and then determining a rate, different credits, different references for each one of those zones, which again was not done in this study that we're looking here. But maybe if that would have been done, we would have seen different results. And quite frankly, I'm not sure in which direction. Maybe the results would be to apply less nitrogen, which perhaps would even increase the differences in NDRE that we're seeing right now, but it would reflect potentially in greater profit at the end. Because even if we're applying variable rate, so imagine that here we're basically taking one reference, which is, we can kind of relate that to the assumption that you have similar yield potential across the field. If that is not the case, which maybe is not looking at this map here, maybe it would have made sense for us to treat the different soil washed areas of this field as a different yield potential, use a different reference, and maybe apply even less nitrogen to those areas because they're not gonna yield as well as the high yielding areas anyways, because of that underlying soil feature or condition of the field. So with that, applying less nitrogen perhaps would create even more stress than what we're seeing on those areas already. But in the end, hopefully, again, the goal here would be to increase and improve profitability, right? So we're applying even less than what would have been applied, even with the variable rates that only assumes one yield potential across the field. Awesome. So I guess a quick summary here. So in this exercise, we did a lot of things. So we imported that UAV imagery in the form of NDRE right before SiteDRESS application. We extracted the reference value, created the grid in this case. Remember that if you have the active sensor mounted on the boom, you don't have to create a grid because it's already sensing and applying right behind it. If we're using imagery of some sort, you do need a grid. So we had to create a grid to create the cells that were receiving different variable rates across the field. We extracted the NDRE average values within each one of those cells. Then we used those values with the reference, which again was just one for the whole field, to calculate the sufficiency index. We plugged that into our VRN algorithm along with the optimum and the credits, created that variable rate prescription, exported as shapefile, and then also checked the effect of the variable rate prescription on our post-VRN imagery. Awesome. So I guess a quick parenthesis here is you can apply this workflow to any imagery, right? It does not have to be drone imagery. We, my team, were using this with drone, with satellite imagery. And we also in our research have the sensor base, the active sensor as well to compare how our prescriptions are changing as we change this sensor type. If you think of it, the most scalable option would be satellite, right? So if you're a grower and you have, I don't know, 20 fields that you want to apply nitrogen, it's going to be harder for you to fly all those fields with the drone as compared to you just getting satellite imagery for all those fields. So the most scalable would be the satellite imagery, although there are other trade-offs, right? Perhaps if you, here in Georgia especially, we have a lot of cloud coverage. So if you cannot get a good satellite imagery for when you need to apply nitrogen, because every time satellite comes around, there are clouds in front of it, then that could be an issue where a drone then could be used to address. All right, any questions or thoughts about what we did today? All right, I don't hear anything, so let me get your attendance. We have a question in the chat. If any of you want to complete the code with map tools. Oh, okay, nice. Thanks, Gonzalo. So Gonzalo here is saying, if any of you want to complete the code with map tools, you can run this code and then it will work. So the code is install.packages. Let me copy this into the script. Thanks, Gonzalo, appreciate it. So if you come here, and you paste this. This is what you have to do to install map tools. So we're just changing the repo where the package is coming from. I'm gonna comment this off, but if you do want to copy this this code, you're welcome to. All right, let me see if I can leave this up and take your attendance at the same time. All right, I just opened the issue for attendance. Make sure to claim your attendance for today. And after that, I guess you were dismissed. I'll stick around for another moment here in case anyone has questions. But if not, then we're wrapped up for today. On Friday, we're going to start working with satellite imagery. So I do want to ask you all that if you will need to have the token, the access token from Planet to be able to pull satellite imagery. So make sure that you receive that. If you remember, we had a class that we applied for the research license, each one of us individually, and Planet probably got back to you by email saying that your application was accepted, that you to create an account and get an access token. We're gonna need that. You're gonna need that on your side. It's gonna be from you. I cannot give you one because that's a personal token. So you have to have yours. If you don't have yours, or if you did not receive it, if you cannot find it, open an issue on GitHub and we can talk about that. But I will come into class on Friday, assuming that you have your token at hand, so we can pull satellite imagery from Planet and start analyzing it. All right, if no one has any questions.
I have a question.
Yes.
I have a question. This is with respect to the final project. When I am seeing the raw data and I'm trying to clean it, there is not, I think almost all the data lines are available. So even after the cleaning it, I think the rows are almost the same. Is it supposed to happen, or do I have to, I'm unable to, make sure what parameters should I clean it up based upon?
So what do you mean by clean?
I mean, there is raw data, and your question number 1 and question number 3, they ask about, showing the data based on raw information and then clean information. So basically, there should be two different sets of data. One is should be raw, one should be clean. And I'm not sure what parameters should I keep in mind while transforming that raw data into clean data.
Well, it's the same as what we did in class, right? So if you just look at those scripts, whatever we did
Okay.
there, the parameters that we use there would be
Okay.
what I would expect that you do on your site.
Okay. Thank you.
Dr. Bastos, I have one more question regarding the final project. I'm doing the usability and we just have one like year data. So we're gonna skip the stable and unstable. We're gonna be just medium, low and high. Is that right? Just make sure I'm not messing.
So that's gonna be up to you all to,
Okay,
yeah.
good. Gotcha. Oh, thank you.
Thanks. Any other questions?
For my research, I have to start Friday after we do that. and we can
Yeah.
Work on due dates and stuff.
Yeah, yeah.
I think there's the end of the 229 pounds, but it.
Okay, so Ujwal is asking, how did I get the N optimal of 229 pounds per acre? So this would, I mean, there are a couple of different ways. The way that the algorithm that was developed and the way that it works is that you would incorporate the local knowledge of the grower into that rate. So that is one way that you can do it. If you have data, if you have yield monitor data, you can use that instead, right? So let's say if you think of it, you could do all the analysis we've done with yield monitor data. So cleaning, wrangling, cleaning, interpolating, creating the stability zones. And you could use those zones if you wanted as your zones for the field. And once you have the zones determined, you can just set the yield potential of each one of the zones using the actual yield data that you have, just like what we did in the previous exercise. So if you wanted to do this in a more, so if you're doing this for a grower and they don't have yield monitor data, maybe you can use their advice of what they've been using in the past, right? If they do have yield monitor data and you want to go that route in determining your yield potential, I guess I forgot to make that connection there. So let me take one step back. So the yield data will allow you to determine the yield potential. So different yield potential areas of the field or zones, and then also using the yield data to see what was the yield potential of each one of those zones, right? So let's say in the end you have the 4 stability classes and you bring the actual yield data and you see that what was the 90th or maybe 95th quantile of the yield distribution for each one of those zones to determine the yield potential in actual bushels per acre if it's corn. So use that yield goal or yield potential as your yield goal in the traditional algorithm. That is basically just yield goal times 1.2 minus any credits, at least for Georgia, right? So that's how you would determine your actual rate that you are going to use in the algorithm to vary around that rate.
So this is the total nitrogen, not the plant.
That would be the total nitrogen required, yes. And then if you have any credits, well, I guess there are 2 places where you can remove credits. One would be on the traditional algorithm, it has yield goal times 1.2 minus credits. So if you remove credits there, then you don't have to remove again on the variable rate algorithm.
So suppose if we apply like 100 pounds pre-plant, then we can subtract 100 pounds in that equation.
Yeah.
And so that 229 will be like 129 here.
Right.
Okay.
Yeah. I mean, as long as you deduct any credits at some point that, you have to do that, right? So let's say perhaps when you're determining most growers, I think, would not consider, like, if you have the fixed rate algorithm that we have here in Georgia, which is yield goal times 1.2, maybe they just do that. So they don't consider any credits at that point. But then when you come in the variable rate algorithm, you do want to consider credits, including the pre-plan application, because the variable rate application is gonna be at side dress time, right? So if you have applied already any previous nitrogen in that season, then you want to remove that credit. Awesome, great questions. Anything else? Any last burning question? Okay, I think we're good then. Thanks everyone. I'll see you on Friday.